Hi, today I'm going to talk about the solutions for Atcoder Beginner Contest 389, problems A to F. And let's start with problem A. For problem A, we have a 3-character string S, and the first and third characters are all digits, and the second character is an X, and we need to find the product of the two numbers in S. So for this problem, we just need to directly get the values from the string and multiply them together. And let's look at the code. So we just input the string and then we find the numerical values of the first and third characters and multiply them together. For problem B, we have an integer x and we need to find the integer n such that n factorial is equal to x. And since x is not that large, it's only 3 times 10 to the power of 18, we can just try all of the values of n from 1 to all the way until we find a value that is equal to x. So let's look at the code for more details. So we first input the value for x and then we create a variable to keep track of the current factorial of n. And initially when I is 0, the factorial is 1. And we can just increment I until the factorial is equal to x. And this will not exceed the time limit because the factorial is only 3 times 10 to the power of 18. And even if we loop until n is 10 to the power of 6, then this would already be way larger than the upper limit for the input for x. For problem C, we have a queue of snakes and we have queue queries to process. And there are 3 types of queries, and for the first one, it is given in the form 1L, and this means that a snake of length L is added to the end of the queue. And for a type 2 query, this is just given in the form of a number 2, and this means that the snake at the front of the queue would leave the queue. So the starting coordinate of every snake in the remaining would decrease by the length of the snake that just left. So there's another type of queries, which is the third type, and this is for us to output the head coordinates of the snake, of the kth snake. So we can use a vector since we need to output for type 3 queries, we need to output the value for the kth snake. So we need to be able to get the snake according to the index. So we need to use a vector to keep track of our queue. And since we don't want to keep popping out vectors from the beginning, since that would take a lot of time, we can just keep track of several variables. One which is j, which we can use to keep track of the number of snakes that has currently left the queue. And another variable we can keep track of is minus, which is the amount we need to subtract for the other snakes, since it will just be the sum of the lengths of all snakes that have already left the queue. And we can update these variables accordingly as we process all the queries. And let's look at an example for this sample input. And so initially, we get a query of a type 1 query that adds a snake of length 5 into our queue. So our vector can be like this, and it can be a vector of pairs, which just stores the head coordinate of our snake and the snake's length. So the head coordinate of the first snake will be 0, and the length will be 5. And afterwards, when we add the next snake, which has a length of 7, the head will start from 5 and the length will be 7. And now we get a type 3 query, and this we need to output the head coordinate of the second snake. And so since our indexes start from 0, 5, 7 is our second snake, and we can just output its head coordinate since the current minus is 0. So we don't need to subtract any lengths from our head coordinate, since none of these snakes have been removed. So we can just output a value of 5. And afterwards, we continue to process the queries, and we get a query of 1, 3. So we need to add a snake of length 3 into our vector. So this snake will start at coordinate 12 and have a length of 3. And afterwards, we continue to add, and this will have these next snake will have a coordinate of 15 and a length of 4. And now we get a query to remove the first snake. So now the first snake is removed. So this means that now there is one snake that is removed, and we need to subtract 5 to all following head coordinates of the remaining snakes. So of the remaining snakes, when we need to output their head coordinates, we need to subtract them by 5 because the first snake has been removed. And afterwards, we get a type 3 query that asks us to output the value for the third snake. So since the value of number of snakes we removed is 1, we can now get the third snake, which would be an index of 3, and it would be here. So the head coordinate is 15, and if we minus it by 5, we can output a value of 10, which would be the correct answer. And so we don't, for type 2 queries, we don't actually remove the value from our vector. We can just increment our count for j and minus. And let's look at the code for further details. So we just keep track of our variables minus and j, and we need to use long to prevent overflow. And for this, we just process all the three types of queries, and for the first one, we just push our new snake into the back of our vector and increment and update the head coordinate of our new snake. And for type 2 queries, we increment the number of snakes that have been removed and the amount that we need to minus for all following snakes. And for the third type of query, we input the index that we want to get for our snake, and since the first j have already been removed, the snake will actually be j plus l. And yeah, that's it. For problem D, we have a circle of radius r that is centered at one of the squares, and we can just consider it as centered at the origin. And we need to count how many 1 by 1 squares can be completely contained inside the circle. So all of these 4 points for any integer pairs ij must be at a distance of at most r from the origin. So for this problem, let's first look at the first sample when the radius is 2. And in this case, we can enclose 5 squares inside this circle. And so we realize that since this is symmetric, we can just calculate the number of squares for the first quadrant, which is highlighted in pink. And so, however, we realize that we can't just multiply the number of squares in the pink region by 4, since some of these squares will be counted multiple times. So we just need to subtract the value that has been overcounted. And so if we look at this larger circle with radius 3, we realize that if we calculate the answer for one of the quadrants for this, then if we multiply it by 4, then the middle square, the center square, will be calculated 4 times, and the squares on the y and x axes will be calculated 2 times. So we need to subtract 3 times from the origin, which is why we subtract 3 in the answer. And we need to subtract the overcounted values from the y and x axes, which is, since the number of squares on the y and on one axis on this section is always r minus 1. So we need to subtract r minus 1 times 4, which will be the overcounted regions here. And so, if we want to find the values for the first quadrant, we can just loop through the x from 0 to r, and then for each, we can use binary search or any other methods to find the maximum y for each x, maximum point. So for x equal to 0, we can find the maximum point, which is this point, that is still in a distance of r from the origin. And we can increment the count for each value of x. So in this case, for x equal to 0, for x equal to 0, we would increment the count by 3 since there are 3 squares. And for x equal to 1, we would increment the count by 3 as well. And for x equal to 2, we will increment the count by 2. So we get a total of 8 squares. And we can just find the maximum value for y using binary search according to each x, and we can look at the code for more details. So I first input r, and then I make a separate condition for when r is equal to 1, since there is only one square enclosed, and for the other times we can loop through, and this loop is what I just mentioned about looping from x equal to 0 to r, and there will be no squares for r, so we only need to loop through values of x from 0 to r minus 1, and the count just keeps track of the number of squares in the first quadrant. And for each x value, we do a binary search to find the maximum y value that is still enclosed in the square. So we can probably also use other methods other than binary search, but I just did binary search. And so for our check function, we need to check if a specific xy is in a distance of r from the origin. So we need to check whether the top right point for our square is inside our circle, since the top right point will be the furthest away from the origin. So we add 0.5 to x and y, and then this part is just checking if the distance is less than or equal to r. And so after we do our binary search for y, we can find the maximum value number of squares that can be contained inside our circle for this current x value, and we can just add that to count. So after we've looped through values of x from 0 to r, we now have a count for the number of squares in the first quadrant. And we can just, as we've described previously, multiply the answer by 4 and subtract 3, which is the overcounted number of the origin point, and we subtract r minus 1 times 4, which is the overcounted number for the x and y axes. And after we've accounted for all the overcounted values, we can just output the answer. For problem E, we have n types of products, and each product has a lot of units. So this basically is a unlimited number of units in stock, and we can buy any amount of units for each product, and if we buy k units of the ith product, it will cost k squared times pi dollars, and our total purchase cost needs to be at most m, and we need to find the maximum number of units that we can buy. So for this problem, if we want to take the maximum number of units in our limited amount of money, we need to take the cheapest units. So since we can take the cheapest units, we can perform a binary search on the maximum amount of money X that we can spend on a single unit of a product. So we can get the price of a single unit for a product, since if we take j units of product I, the price of the jth unit will be equal to the price of j units summed up together subtracted by the price of j minus 1 units. So this is equal to 2j minus 1 times pi. So 2j minus 1 times pi will just be the price of the jth unit of product I. So this means that for each product, we can get the price for each of its units. And so if we want to perform binary search on the maximum amount of money, we can just create a check function to check if it's possible to get all of the units with prices less than or equal to X. So if the amount of units, the total price of all of these products with prices less than or equal to J is already greater than our maximum value of M, then this means that the current value of X doesn't work, and we need to find a smaller value. And however, if it works, if the total price is less than or equal to M, then we can find a greater value for X and include more units that we buy. So let's look at the check function for the binary search. So for the check function, we can just loop through all of the products from 0 to n. So if we loop through all of the products, we can count for each product. We can add all of the units that has a price less than or equal to X. And so if a unit has a price of less than or equal to M, then this means that if we get j units of the current product, then this means that 2j minus 1 times pi, I is the current product, needs to be less than or equal to X. And if we move everything over to the left side, then we will get 2j minus 1 is less than or equal to X divided by pi. And if we move 1 over, so 1 plus and divided by 2 is greater than or equal to j. So j can only be less than or equal to this value. So we need to take the floor of this value to get the number of units that we buy for the current product. And we can add the price that we need for buying j units of this product. And if the total price after we look at all of the n products is greater than M, then this means that the current X, which is X is the maximum amount of money that we spend on one unit And this means that the current x value does not work and we need to get a smaller value. And so this can help us check whether the binary search, how to perform the binary search. And so for the remaining amount of money, since after we purchase all of the items for price of x, we still have a remaining amount of money that we can use to purchase as many items with price x plus 1 as possible. So in this case, we wouldn't need to consider items with prices, any items with units that are greater than x plus 1, because now all of the units with prices x are counted for. And if all of the units with prices x plus 1 can also fit in the total price of m, then our binary search would not have resulted in our value of x, since our binary search finds the maximum value of x that is possible. So if we found the value of x, then this means that we cannot include all of the values of all of the units that has a price of x plus 1, since if we could, our binary search would have resulted in a larger value. So we can just safely add all of the items with prices x plus 1 and add as many of them as possible. And next, let's look at the code. So this part is the binary search that I mentioned about the value of x, which is the maximum price that we can spend on a single unit of a product. So the check function is also what I mentioned previously, that checks for the loops through each value, each product, and finds the maximum number of units that we can buy that's still in the range of x, and we can just add the price for the j units of the product that we buy and increment the count. So the count just keeps track of the current number of units that we have, and if the price is already greater than m, then we can just return the value, since this is already impossible. And so if a is less than or equal to m, then this means that this is possible, and we can update the first and last values accordingly. And afterwards, the binary search will actually find the first value that does not work. So we need to subtract first by 1 to ensure that this is the value that works. And afterwards, for the remaining amount of money, since this pair just returns the price and then the number of units, we can get the remaining amount of money by subtracting m by the first value of a. And answer is the current number of units that we have, and we can add answer by the r divided by first plus 1 will just be the maximum value of the maximum number of units with prices x plus 1 that we can get. So afterwards, we can just output the answer. And we also need to be sure that we use int 128, since I used long previously and got a lot of errors with the overflow stuff. So yeah, just make sure that you use a large enough value so that the numbers don't overflow. For problem F, we have an Atcoder contest, and if in the I contest the rating is currently between L and R, the Takahashi's rating will increase by 1. So we are given Q queries and each query in X value is given, which is Takahashi's initial rating before any of the contests, and we need to determine his rating after he participates in all of the N contests. So for this problem, we can keep track of a value fi, which is if Takahashi starts with a rating of I, what is his rating after J contests? So fi represents his rating after J contests, and we can just process all the contests in order from 1 to n. And in the end, after we've processed all the contests, fi would just be the value, the end rating after all of the n contests if he started with a value of I. So we notice that f is always increasing, so fi plus 1 can never be less than fi because initially they all start in increasing order, and if one value adds 1 to become the other value, then they would move together. So for example, if in this case below, when we add all of the values in the range 1 to 5 by 1, then we will get 2, 3, 4, 5, 6. And afterwards, if we have to update a value for 6, then these two 6s would move together, so they would increase by 1 together, which means that any f that is greater can never be less than value for I. So fi plus 1 can never be less than fi. And so for each contest, we need to update a range of f that has values between L and R. So since we need to update a range quickly, we can use a range update segment tree, so a lazy update segment tree. And to find indexes in f that is greater than or equal to L and less than or equal to R, we can use binary search. So we can use binary search to find the left index of the range that has a value included in L and the right index of our range. So, and then afterwards we can update values from this left index to the right index. So if we look at the sample input, we can look at the first sample input, and initially there are values. All the x values will be listed like this, and each value corresponds to the initial value. And after the first contest, all of the ratings in the range 1 to 5 will be updated. So in the range 1 to 5 will be incremented by 1 using our segment tree. And we will add all of these values by 1. And then after the second contest, all of the ratings in the range 1 to 3 will be updated. So these two ratings will be incremented by 1. And in the third contest, ratings in the range 3 to 6 will be updated. So all of these, since they are in the range 3 to 6, they will be incremented by 1. And this is what I just mentioned previously. Since the values of 6, once they are together, they will continue to increment together. So f will always be in increasing order. And afterwards, the next contest, we update values in the range 2 to 4. And so the only rating that will be updated is this one. And for each of these, we find the left and right index using binary search. So for example, for the first one, we update values in 1 to 5. So we find this index and this index using binary search on the segment tree. So we perform binary search on the segment tree and then update the range that we find. And afterwards, we continue to update the last one. And we use binary search to find the first value that's included in L equal to 4 and R equal to 7. So this is the value that we find for binary search on L. And if we perform binary search on R, we will find this value, so we can update the values in the range 1 to 7. And afterwards, after we've processed all of the values, we can now process the queries and just print out the answer for each of the queries. And for the code, the top part is just all the segment tree stuff, and build is just to build our segment tree with initial values of fi equal to I, and in this case we just update our segment tree with the initial values. And afterwards, we process all the contests to get the value of f after each contest. And for the find L and find R, we just use binary search to get the index for L and R, as I've mentioned previously. And for my query, I just did a query for the maximum value in the region, in the range. So since f is in increasing order, a query from 0 to the current index will get the value of the current index. So for each, I just query from 0 to mid. And so this way, I wouldn't have to push down all of the values, which would take a lot of time if I just find the value for one index. So I use a range update to add, and for my query, I use a range query for the maximum value in that range. And so after we find the L and R, we just add all of the values in this range by 1. And since after we process all of the values for the contest, we can just output the answer for each value of x.